In this video, we're going to look at vectors and some of their basic operations. Many of you have learned about vectors previously in different classes. Occasionally, there's a couple 5C students who have not had vectors. But I'm going to go through this rather quickly. If this is not in-depth enough for those of you that haven't learned this before, there's plenty of videos online that talk about it in detail. Right? So what a vector is it's a mathematical object that allows us to tie two pieces of information together. Oftentimes we have a physical force, perhaps, where we want to tie together the magnitude of that force together with the direction. So for instance, if I have some sort of object here and I'm pulling on it with a certain force, then I want to be able to represent that force, how hard it is and which direction I'm pulling it. So for instance, a force like this, I'd want to have a way to represent that first force is stronger than the second force, for instance. So a vector is a way that we can tie together magnitude and direction. Direction being, are we pulling it up? Are we pulling it this way? So for magnitude, we're going to express the magnitude by how long the vector is. We're going to draw a directed line segment, an arrow if you will, but a directed line segment, and we're going to have its relative length correspond to that relative force. So maybe this is a force of 40 pounds, maybe this is a force of 20 pounds. And to specify the direction that we are pulling it, for now, we have to give some sort of reference angle, whether it be from horizontal, from vertical. For now, in math, we'll use the angle in standard position, so relative to the positive x-axis. Okay, so where do these come up in math and physics and engineering? Well, one place is, and a very big place, is what I just said, a force. Another would be, for instance, if I have an airplane flying along here at 400 miles per hour, and we have a wind blowing here that is maybe 50 miles per hour, right? Then the speed of that plane and the speed of the wind, we're going to represent that by how long that vector is. So this one much longer than this velocity much greater than that. And so we are interested in knowing what direction that the plane is going and how fast, those two things together, right? Sometimes you'll see, you've probably seen something like this before. If you just look at this and think about what does that look like, it's representing, to me, it kind of looks like maybe it's representing some wind patterns or some water flow patterns, some current patterns. And without even really knowing what vectors are, it would look to me like these arrows are longer than these in here. So maybe there's a faster flow here and a smaller flow here, and there's maybe a little whirlpool going on. This is actually something we're going to study in the last chapter. This picture right here, it's an example of what we call a vector field, but we'll get to that in chapter 16. All right, so for a vector, we want to be able to represent magnitude and direction. So the magnitude we're going to talk about by the length of this directed line segment. So directed line segment, we call this the initial point, and this is the terminal point, so start and finish point, right? For a vector, instead of using, we're so used to using variables like x and y for real numbers, a vector is a different object. It's a different entity. And so we want to label it different. So the way we represent the idea that we are talking about a new entity is we put an arrow over it. Now I often do just the one-sided arrow because it's quicker, but that's vector notation. So anytime you have a vector, you're going to want to put the arrow over it so we know we're talking about a vector, not just a number. In a book, the way they represent a vector is to use boldface. But rather than having to change my pencil every time or draw really thick, we use the arrow on top. The magnitude, I already said, the magnitude is the length. We are going to use the length to express relative magnitudes. And the notation that we're going to use for magnitude looks like this. Now, your book uses this. And for vector notation, it's interesting because not all books are universal. So you can use either. I mean, that's less writing, of course. But sometimes when you write this, students think absolute value, and we don't have such thing as an absolute value of a vector. But so I like to use this one, but either one, you can use either. Okay, the direction I mentioned above, we usually have to, for the direction, we need to give an angle. So we need to have something measured relative to some sort of angle. So, you know, when we do navigation, sometimes we measure from the north. Maybe we have a bridge truss, and we're going to give the angle from the truss. So in real life, you'll be given some sort of indication about direction. But in math class, unless otherwise stated, the direction is, like I said up there, given from the positive x-axis. Equal vectors are vectors that have exactly the same length and magnitude. Exactly the same length and magnitude. All right, so if we want to kind of quantify vectors, assign some numbers to them, we can superimpose a coordinate system. And what we do is we superimpose the coordinate, when we superimpose the coordinate system, is if I put the initial point at the origin, and then I look at what the coordinates are for the terminal point, we would call that vector 3, 1. Now, it doesn't mean that it has anything to do with the point 3, 1, because what we just said about equal vectors is all they have to have is the same length and direction. They don't have to have the same position. So that means anything that has this same length and direction would be called vector 3, 1. So all of these. So all of those represent vector v. So this is vector v, and this is vector v, and so on. This is vector v. They're all vector v. So point of application, this is actually comes up a lot. So let me just write it down. Point of application is not defined for a vector. So when I say I have the vector 3, 1, it doesn't mean I'm talking about that specific vector. It's anything that has that go to the right 3, up 1. Go to the right 3, up 1. Sometimes we are interested in a specific vector. When we're interested in a specific version of v, then we would look at PQ. Now PQ is the vector 3, 1, but in this case, because I'm labeling initial and terminal point, those points, then it ties it to that location. All right. If we're given 2 points, P and Q, and we want to find the vector that goes from P to Q, so we want the vector notation from that. So if you could picture taking this exact vector and sliding it up so its initial point is here, then we'd want to know what is the terminal point. The way that we're going to find that out is we're going to take the terminal points coordinates, subtract the initial points coordinates. So AB is going to equal x2 minus x1, comma y2 minus y1. So we subtract, and you have to be careful, it's Q points minus P points, because that direction from P to Q, that's important. So for example, if I said, here's a point, -3, -1, and here's the point 2, -2, and I wanted the vector from P to Q, that PQ, from P to Q, the x coordinate is the change in the x component. So 2 minus a -3, 2 minus a -3. And the y is the change in the y component. So -2 minus a -1. So if I'm careful with all my negatives there, that would be 5 and -1. Now you can see whether or not that's reasonable. What that's saying is horizontally, the x component, if you will, horizontally 5, and the y component, that's vertically, is 1. So from here to here, we would be going to the right, 1, 2, 3, 4, 5, and down 1. Okay? In some problems, what they'll do is they will give you these 2 points and ask you to find the components. Sometimes you'll see you're given 1 point and the components, you go back and find this, but it's all related by that equation. So we talked about a vector is a magnitude and direction information given together, and we can express it in magnitude and direction form. We can just say what the magnitude and direction is, and that'll tell us what our vector looks like. Or we can give the components, and that'll tell us what our vector looks like. So we want to be able to convert back and forth from magnitude and direction to component form. So suppose I give you, for instance, magnitude of the vector and the direction, and so suppose then you wanted to find the components. So magnitude and direction to the components. So the components here, if I wrote this as the point AB, and I drew vertical and horizontal and vertical here, so this would be A and this would be B, then we can find the relationship between A and B and magnitude of B and theta just using our trigonometry. So in my picture, as I have it drawn, the cosine of theta is the adjacent over the hypotenuse. So A equals magnitude times cosine theta. And similarly, for B, we have opposite over hypotenuse is sine of theta. So B equals magnitude of V sine theta. It's very similar to what you did when you worked with polar coordinates back in Math 5B. So the vector V can be expressed as magnitude of V cosine theta, magnitude of V sine theta. It's important, though, that this is if theta is in standard position. Okay? So for example, suppose I told you that we had a vector whose magnitude was 5 and whose angle theta was, magnitude is 5, and angle theta, say, was 30 degrees. So that would look roughly like, what is 5 units long? Say 5 units long, angle is 30 degrees, so something like this. If I superimposed it onto the coordinate axes here, the length is 5, this is my scale here, this is 5 units, and so 30 degrees out would probably be something like this. So my vector probably looks something like that. Okay, so to find the components then, we just have our vector is going to be magnitude of V, that's 5, times the cosine of 30 degrees, and 5 times the sine of 30 degrees. So that's going to be, cosine of 30 is radical 3 over 2, so 5 radical 3 over 2, and 5 halves. So very straightforward to find the components if you're given magnitude and direction. But the one caution, as I said, was you have this formula only works if you're given theta in standard position. And the reason why I mention that is because when you're doing physics and engineering, a lot of times you're not given the angle relative to some positive x-axis. You're given the angle relative to things like, I said the angle of a bridge on a truss or something. Maybe you're going to be given this angle instead. Maybe that's the angle that you have measured. Or maybe they're going to tell you it's the angle here from north. So if you want to find this horizontal change and vertical change, and you're not using that angle, then you have to either take the angles they gave, figure out this standard position angle, and you can use the formula. Or what engineers typically do is they go with the angle they're given and they use their trig with that angle. So for instance, if I was given angle beta, you can draw in a right triangle right there. In this case, A could also be labeled up here. That's the horizontal change is A. So if I was going to use the green right triangle, then I would have that A is opposite beta. So sine of beta is A over magnitude V. Sine of beta is A over magnitude of V. So A equals magnitude of V sine of beta. Now, I don't want this to confuse you. Typically in math, we talk about theta in standard position and we can use this formula. But when I went on to physics and engineering after taking math, and they started telling me the x component has a sine in it, that kind of threw me for a loop because I was used to x component has cosine, y component has sine. But it depends on what angle you're given. Okay, if this is the angle you're given and you want to work with that, in this case, this horizontal is opposite, so opposite is sine. Okay, so just wanted to point that out because in the math book, you see this all the time, and then you head over to physics and you start seeing this. They're just using different triangles, different angles. Now going backward from component form to magnitude and direction form is a little bit trickier. So if I'm giving you the component form, so if I tell you that my vector is AB, that means change in x, the horizontal there is A and the vertical is B. And if you want the magnitude of this vector here, so I want to find the magnitude and the direction. So let's call this our theta, standard position. So to do that, again, it's just trig. So, and actually Pythagorean theorem. So the magnitude of that vector is a squared plus b squared square root. Just using Pythagorean theorem. And then if I want to find theta, the tangent of theta equals the y component, the y component, which I labeled b here. So b over a. Okay. Now, the only reason that you have to be careful with this is because this formula does not tell us what theta is. It tells us what the tangent of theta is. And when I go from tangent of theta to theta, if I'm going to use the inverse tangent, I've got to be aware of the inverse tangent restrictions. Okay, now you should know this quite well from Math 5B, but I'll show you in an example to see if you're on board with me. Okay, so suppose I gave you the vector v equals negative 5, negative 5, sorry. Negative 5, negative 5. So negative 5 would look like this. That's my vector. Then the magnitude, and leave myself any room to write here, the magnitude of v equals the square root of negative 5 squared plus negative 5 squared So 25 plus 25. So 50. So 5 radical 2. That's not the part that's a little tricky. So the length of that is 5 radical 2. Where we have to be a little bit careful is, I'm just going to write right here, tangent of theta equals the y component over the x component, so negative 5 over negative 5, which is 1. So the thing is, the tangent of theta equals 1. How many solutions does that have? That has, tangent is 1 here at the 45-degree angle, but also down here. So that means theta could be pi over 4 plus pi times k, where k is an integer. There are infinitely many solutions. But we want very specifically this one, or this one, doesn't matter, but we want an angle measured from the positive x-axis, okay? This one up here in the first quadrant, that's not the one we want. We want an angle corresponding to the one in the third quadrant. So we don't want this. We want to know tangent of theta equals 1 and theta is in the third quadrant. And so that means that we're going to have we could either use this angle here, 5 pi over 4, or we could call it negative 3 pi over 4. But it's not pi over 4. So I can't just say, okay, tangent of theta is 1. Let me put this in my calculator and say theta equals the tangent inverse of 1. The tangent inverse of 1 is pi over 4. That is not the angle that we need. So we can't just write that in terms of the inverse tangent. So that's what I was trying to say earlier, is that when you have tangent, there's infinitely many solutions, but you need the theta that gets you where your vector is. So you actually have to know what quadrant this vector is in, or pointing, what direction it's pointing, and find the corresponding angle. So that's key. And you've come across this before. I'm sure that you have, either when you were learning about your inverse trig, or if you've learned vectors before, or when you learned polar coordinates. All right? So where you have to be careful a lot of times is when the numbers aren't quite so neat, I suppose, like, well, I say neat, this is very neat. Negative 3, 4. Negative 3, 4 would be something like this. And so the magnitude, this is what I was talking about, very neat. This is square root of 25, so 5. Tangent of theta equals the y component over the x component. Now, when we get to a situation like this where it's not an angle we know, this one we know exactly, we should know exactly. So usually students are pretty good about getting the right answer there. But in this one, we don't know this exactly, and so we pull out our calculator. And when we pull out our calculator, we tend to go, okay, theta equals the inverse tangent of negative 4/3. But that's not correct, because inverse tangent always gives us something between negative pi over 2 and pi over 2. If the tangent is negative 4/3, those of you that like the unit circle like I do, then that means negative, it means it's either in the second quadrant or the fourth quadrant. When I take the inverse tangent, it gives me that one. That's not the one I want. So it's okay, we're going to use that, but we're going to adjust it. So we would need to, for our angle, we would need to take that angle and add pi to it. This is a good time to tell you that in this class, and in most math classes. We like exact answers. And the reason is that we get a lot of round off error when we start putting things in our calculator too early. So if we algebraically work it through and get exact answers and then just put it in the calculator at the end, then you're going to have much better accuracy. So in math, we typically ask you to get exact answers all the way to the end just to make sure you really can do the algebra that gets you there. Okay? So that's converting back and forth. The next thing I want to talk about is vector operations. Vectors are not numbers, they're a brand new type of quantity. And so if we want to talk about what it means to add or subtract or multiply vectors or take the absolute vectors or any of those operations we're so familiar with, we have to define what we mean by that operation first. So for instance, I threw in the terminology, take the absolute value of a vector. That's actually not an operation that's even defined. All right, so vector operations. The first one that we are going to look at is addition. Vector addition is really helpful in applications. And so what I'm going to show you how to do is to think about vector addition both in terms of just magnitude and direction, which means no coordinate system, no numbers or anything, just the arrows, if you will. And then we'll also look at how we would do this with components. Right? So if we're going to define vector addition, I'm going to call this vector here V and this one W. So define vector addition, we could do it in two different ways, and they're both useful. They're both going to give us the same results, but they're both useful depending on what physical application we're talking about. So tip to tail looks like this, tip to tail. If we're going to look for V plus W, we take V, and then we draw a photocopy of W following V. So I'm going to try to draw here something that looks exactly like W. I guess I actually could cut and paste, but that's quicker. So for tip to tail, the vector sum would be from the beginning of the first vector to the end of the second. That is V plus W. If we want to do it with the parallelogram method, there's our V. Again, we're going to draw a representative of W, but instead of following V like this, we line up their initial points. So if I line up their initial points and draw the representative of W here, then we form a parallelogram out of those two vectors as best we can, where those are the corner. And then the vector sum is defined to be from that like initial point out to the other diagonal of that parallelogram. Now you'll notice that those two blue vectors, they should look like the same vector. And remember, the same vector means same length and direction. I guess this could be a little misleading the way I drew this. The end of that vector is not there. I kind of put an arrow there, but the end of the vector is here. So they should look same direction, same length. So why do we have two different ways of talking about it? Well, they're just useful. They're both useful in physical applications. A lot of times I use this one when we're talking about, for instance, if this was an airplane and this is the path that it's trying to take, but the wind is doing this, then this would be the actual path of the airplane. Same with, trying to swim and the current takes you, this would be your actual path. This one is often used when we're talking about applying a force to an object. So for applying a force to an object, we think of both of them as being connected to the object. And so if this person is pulling with a certain force and this one is pulling with a certain force, this vector represents the net force. So if this was two different people pulling at these two different lengths, different magnitudes, then that would be equivalent to one person pulling with this longer magnitude in this direction. That's called the resultant force. So the visual geometric way of adding vectors is useful. It's useful to get a feel for what you're expecting in the physical world. But in terms of computation, it's not very accurate. So how do we add vectors when we're talking about components? Well, the definition here says that if we're going to add two vectors, you just add their first component together and their second component together. Now, that's probably the way I would have invented it myself, but it's not done that way because that's the way we might think that it should be done. It's done that way because it gives us useful physical computations, and I'll explain more what I mean by that as we go on. But for instance, in this example that I have here, if I gave you these two vectors and I said, draw for me the sum. So if we're just drawing the sum like we just learned how to do, I guess I'll label these V and W. Since their initial points are already lined up, then I'm going to use the parallelogram method. So I'm just eyeballing this. I could do a better job. Because since there's graph paper underneath there, I can see that it's 1, 2, 4 units to the right and 2 units up. So from here, I just go 4 to the right and 2 up. But I'm not wanting to be that careful. I'm just eyeballing it. So I am guessing that the vector sum is going to be about like this. Now let's actually compute it. Vector V, if we look at vector V, the components of that, it looks like it ended at the point -3, 1. -3, 1 are the components for vector V. And vector W, the components are, what do we got here? 1, 2, 3, 4, 2. So 4, 2. So according to this definition above us here, V plus W would be just to add these components and add these components. So -3 plus 4 is 1, and 1 plus 2 is 3. Oops. And so we would have the vector 1, 3. And if I were going to draw the representative of the vector 1, 3 from the origin, it'd be 1, 1, 2, 3. And that's actually pretty close to where I drew it, although I sort of missed where I should have drawn it. But so I just wanted to show you that both the visual geometric way of doing it and the computational way of doing it, it will give you the same thing, but they each have their purposes. The next computation that we're going to look at is scalar multiplication. And scalar multiplication, you can kind of already guess based on what I was telling you before when we were talking about forces. If that represented a force of 20 pounds and I said, now let's represent a force of 40 pounds, it just would be natural to just make it twice as long. So if this is V, what we're going to mean by 2V is something that is twice as long. What we're going to mean by, say, a half V would be something that's half as long. For scalar multiplication then, by the way, the word scalar, if you've not heard that before, when you start talking about an entity that's not a real number, so like a vector or matrix, when you're now talking about real numbers, to emphasize that it's not a vector, we call it a scalar. All right, so this number actually scales that vector, half as long, twice as long. And if we wanted to multiply it by a negative number, think about it this way. Here's a force V. The negative of that force, it would make sense that instead of pulling it upward, we're pushing it downward. So the negative of that force is just going to go the other way. So that would be the negative of the force. So for instance, -3V would be something 3 times as long in the negative direction. So that's a scalar multiple. The way we do that using our components is we just multiply each of the components by that scalar. All right, so you can try that out, maybe even do what I did here, with this picture, just to really see if you believe it, maybe find 2 times V and see what it looks like. All right, subtraction of vectors. Once we have addition and scalar multiplication, we get subtraction automatically. So when we subtract, if I wanted v minus w, I can think of it as addition as v plus the opposite of w. So if I wanted to think of it that way, then I take my opposite of w. So if this is w, opposite of w looks like this. I guess I should label that w. There's w. This is v. So if I wanted to add v plus a minus w, I'll draw the minus w either tip to tail or parallelogram. I'm going to go parallelogram. We draw in the parallelogram. This is minus v. And then for addition, we draw the diagonal there. So that would be v plus a minus w. So in terms of doing subtraction geometrically, you can just change it into an addition problem. Then you don't have anything new that you need to learn. But if you wanted to be able to do subtraction geometrically directly, we have the parallelogram method. And the way the parallelogram method works is just like the first part is just like addition. You get your v and your w, and you draw the parallelogram. And with addition, remember, it was this diagonal here. With subtraction, it's this diagonal here. Okay, so, whoops. Okay, and then but which way is it going? It goes, when you subtract v minus w, it always goes from w to v. V minus w goes from w to v. Now, the way I remember that, whoops. The way that I remember that one, if I forget that it's this one to this one, is that if you look at adding these two, if you added these two tip to tail, algebraically, doing your algebra, you'd have w plus v minus w. W plus v minus w is v, so it all works out. Algebraically, I'm not going to write it down here, I'm out of space there, but algebraically, here I can put it right up here. If you want to subtract, you just subtract components. So pretty straightforward. Here are some properties of vectors. I'll let you take a look at them. Those of you going on to Math 10, you're going to be doing a lot with properties of vectors. You're going to be studying vectors quite a lot. The zero vector, it's hard to tell that that's what this is, but it is bold. It's a bold zero, so we would have to write it like that. It is just a vector composed of zero coordinates, components there. And you might look at these properties and say, we already know this. That's just the commutative law. That's just the associative law. But we don't know it because these are brand new entities, and we can't assume that what is true for real numbers is going to spill over into vectors. In fact, there are lots of things that don't. In terms of proving properties of vectors, they're about as easy of a proof as you can do because, let me show you how proofs of vectors work. Let's suppose I'm going to prove the first one. All right, so in the proof, I just need to, first of all, define two variables. Let A be A1 and A2, and let B be B1 and B2. Okay, so you have to define them. That's part of the proof. Then A plus B is A1, A2 plus B1, B2. And that's defined as A1, plus B1, A2 plus B2. And where we're trying to head is that equals B plus A. Now B plus A, let me just scribble down here for a minute. B plus A would be B1, B2 plus A1, A2, which would be B1 plus A1, whoops, B2 plus A2. So we have to somehow get from here to here and come on back in. But really we're there because A1 plus B1 is the same as B1 plus A1. And you might look at that and say, well, how come you could do that there and not here? Because once we are inside the vector, then you're just doing operations of real numbers. And so I just use the commutative property of real numbers there, once you're inside the vector. And so then we can just continue on what we said here. So once I have that, using the definition of vector addition backwards, right? The definition says add and add, so we can pull apart. And then this is vector B, and then that's vector A. And so we really have tied them together. So that was a pretty simple one, but the idea is how most of these vector proofs work. Assign the vector some general variables. By the way, you have to do a general. Sometimes when I ask for a proof like this on the test, somebody will say, well, let A be 3, 1 and B be 4, 7, and notice when I add them, both directions they're the same. That only proves it for those two vectors. If you're going to make a general proof, you have to use general variables there. So usually what will happen with any of these vector proofs is you go ahead and define your general vectors and then do the operation, and then once you're inside those vectors, you get all the properties of real numbers and you're on your way. All right. Unit vector. So a unit vector is any vector whose magnitude is one unit. Right? Now we talk about some specific unit vectors, and because we talk about those a lot, sometimes we forget that the general unit vector is any vector whose magnitude is 1. So for instance, suppose I have V equals 3/5, -4/5. The magnitude of V is 3/5 squared plus -4/5 squared, and I'll let you do that arithmetic, but we end up getting 1. So that is a unit vector. But we have some special unit vectors. They're called standard basis unit vectors, and they are the two that go along our coordinate axis. So if I just go 1 unit horizontally, so we have the vector 1, 0, we call that I. Some books use this notation. When you know you have a unit vector, you put this little hat on it instead of the arrow. Now, I don't think that's in our book, but just in case you ever see that. And then going here, if I go 1 unit in the y direction there, 0, 1 right here, then we call that J. So those are our standard basis unit vectors. And all vectors can be written in terms of those. Those of you taking Math 10 or going to take Math 10, if you've taken Math 10, you've already learned that basis vectors are vectors from which you can build up any of the vectors in your space. So I can find any vector by taking the linear combination of these two. So what I mean by that is if I take vector V and I take, let's see, what is this vector V? Anyway, 1, 2, 3, 4, 2. So in my picture, vector v, actually, let me go back, sorry about that. I didn't want it to be anything specific. I can count squares in my picture and see that it's 4, 2, but I'm just trying to generalize here. So vector v is AB. That means we're going to go like this and like this. We can think of adding those two vectors. This blue vector here is A times I. Oops. A times I. Because remember, when we multiply a vector by scalar, it just changes it by that, that scalar amount, changes the length. So if this is I, A times I would be this stretch or shrink in that direction. And this vector over here would be B times J. J is the unit vector here. B times J is going to give me a vector of length B, so the vertical component in the direction of I there. And then using the parallelogram law that we saw, if we added the red and blue vector, we would get, if we added this, we got our parallelogram, this would be the sum. So that vector AB is the sum of AI plus B times J. Now, a lot of times we kind of lose sight of what this is all about. First of all, notationally, notation, you can write a vector as AB or as A times I plus B times J. Those two are interchangeable. A lot of books tend to use this. I tend to use this, just a little less writing, but interchangeable. So if you had V, say, equals -3, 2, you could also write that as -3I plus 2J. Either way is fine. So why even have this way if this is less writing? This way really just emphasizes the idea that you can break a vector down into horizontal and vertical components. And that's used a lot in physics and engineering. If you had some force acting on an object and you wanted to break it down to the amount of the force that's horizontal and the amount is vertical, for instance, this just emphasizes that. So we've seen how the unit vector I and j can act as building blocks, and we can write any vector in terms of I and j. But in the same way, we often need building blocks in the direction of a specified vector. So for instance, in this example here, I have the vector -3, 4, so -3, 4. That's not a unit vector. Unit vector would be something that is, 1 unit long. This is way too long. In fact, how long is it? The magnitude of v equals -3 squared plus 4 squared, which turns out to be 5. So this vector has length 5. I want a vector that's that same direction, but only length 1. I'm going to call it u, unit vector. So I need something that is 1/5 as long as v. Right? So my vector u would be 1/5 as long as v. Because that's how scalar multiplication works. If you have vector v, and then you multiply by scalar, your new vector will be 1/5 as long as the original. So that will give me one of magnitude 1. And so that's going to be 1/5 of -3, 4, which is -3/5, 4/5. And you could check that. You could check that if you took the magnitude of that, it does in fact equal 1. By the way, back up here, I should have had magnitude. So you can see that in this problem that when I wanted that unit vector, I took 1/5. Well, that was 1 over the magnitude of v times v. And that'll work every time. If you think about why that worked, that'll work every time. A unit vector in the direction of vector v is going to be to take 1 over the magnitude of v times v. A lot of times we think about it as v divided by the magnitude of v. And it's okay to think of it that way. We just never formally define scalar division. So this is technically what we're doing. So we end up needing to do that a lot because those unit vectors are building blocks. Suppose I continued this problem and I said, now what I want you to find is a vector of length 7 in the direction of v. So if you wanted a vector of length 7 in the direction of v, and actually what I'm going to do is redraw what I just had here. So this is v of length 5, and then u is here of length 1. And we want something now that's length 7, so longer, okay? And I'm going to call that vector w, and we want vector w to have length 7. Well, the easiest way to do that, well, I shouldn't say easiest, you can go straight from v to w. But typically it's easier to go from v, find a building block of length 1. From length 1, from the blue vector, how would we get the red vector? Vector w is just going to be 7 times vector u. The length of u is 1, so 7u would have length 7. So that's going to be 7 times the vector we previously found. So negative 21 over 5, 28 over 5. So that's how we can sometimes use the unit vectors as building blocks. Now you might have said, I could go directly from v to w by multiplying by 7/5. You're correct, you could. You could have said w equals 7/5 times v. You would be dividing by the 5 and multiplying by the 7 at the same time. I did in 2 different steps. All right. Vectors can also be used to show directions of lines. So find a vector parallel to the line 3x plus 2y is 6. What is that line that goes through 2 and 2, 3, like so? This line here. So we'd be wanting some sort of vector in the direction of that line. Now, I don't know which way it points. It could point either way. But in the direction of the line would mean parallel to that line. This is done often as we go on as well. And the way that we can do that is use the idea of slope. If I find the slope of this line, the slope of this line is negative 3/2. And remember what that means. Negative 3/2 means change in y over change in x. So we're going to go down 3 and to the right 2. Down 3 and to the right 2. Well, a vector that goes down 3 and to the right 2 would have a y component, I'll call this v, it would have a y component of negative 3 and an x component of 2. Also, let me draw this one in another color. I can also think of a slope of negative 3/2 as being a slope of 3 over negative 2. So we could think of it as up 3 to the left 2. So if I thought of this vector as going up 3 to the left 2, and I'm not drawing it to scale here, up 3, I guess I could, up 3 and to the left 2, then that vector, I guess I'll call it v2, would have an x component of negative 2 and a y component of 3. So either one of those would give me a vector parallel to that line. Now, if you notice the relationship between the two of them, they're just opposites each other. Right? Multiply this by -1, you get this. So in general, if the slope of a line is, say, A over B, then a vector in the direction of that line, or you could think of it as parallel to that line, is change in y over change in x. So the change in y is A, the change in x is B. Change in y, change in x. Vertical component, horizontal component. And we could have plus or minus that. Here we're going to look really quickly at an application. Vector applications are so much fun. We do some of them in our trig class here. There is a class called statics, which any of you engineers, especially mechanical engineers, you'll take a class in statics. You do a lot of vector applications in a physics class, so you maybe have already done a lot of applications like this. We're not going to really get into the applications in this class. We're going to be just using vectors as a tool to do something else. But I just want to give you at least one example so you can get a feel for how useful vectors can be. By the way, if you get a chance to take that class, I think it's Engineering 14A, might be 15A. That was a lot of fun. I took it when I was a new student here just to get more applications under my belt, and I really enjoyed it. Okay, so in this example, we're being asked to find the resultant of these two vectors. And so if I just use my sketching idea here, draw the parallelogram, I would say the resultant of those two looks roughly like that. And it's a good idea to draw that picture, so I know what I'm expecting to happen. So what they're asking us to do is take the sum of those vector forces. Now, in order to do that, what we have to do is to put each of those forces in component form. So if you remember, V is the magnitude of V cosine theta, magnitude of V sine theta, if theta is given in standard position. So force 1 here, the magnitude is 40 newtons. So 40 newtons cosine 30, 40 newtons sine 30. So 40 cosine 30, 40 sine 30 degrees. Cosine of 30 degrees is 1/2, so 20. Whoops, no, it's not. Square root of 3 over 2. Cosine of 30 degrees is square root of 3 over 2. Sine of 30 degrees is 1/2. So those are the components for F1. F2, the magnitude of F2 is 60, and the direction angle is given there as negative 45 degrees. And so F2, cosine of negative 45 degrees is square root of 2 over 2. So 30 square roots of 2 and negative 30 square roots of 2. And so if I add these two, I'm going to get 20 radical 3 plus 30 radical 2, 20 minus 30 radical 2. And that's the exact value. And as I said, in math, we like to go ahead and use the exact value. Now, I'm not opposed to also finding an approximation just to see if we think our answer is reasonable. So by my calculations, that would be approximately 73.7, negative 16.2. It's possible that's an incorrect computation, but let's go with it. So does that make sense? Well, that's the beauty of having drawn what I believe the resultant should be. And in my picture, it looks like it should be to the right and down, so positive, negative. So that's reassuring, right? Now, this, when you're doing a resultant problem, when you're doing a physical problem, you're usually given vectors in magnitude and direction form. We compute them to component form so that we change them, to component form so we can do the computations, but we answer in magnitude and direction form. So the magnitude of R is the square root of first component squared plus second component squared. Square root, again, exact. And I'd like to get an approximation too, to be real world. The tangent of theta is 20 minus 30 square roots of 2 over 20 square roots of 3 plus 30 square roots of 2. Now I can see that the resultant is in quadrant 4 here. And so when we take the inverse tangent, it always gives us something either in quadrant 1 or quadrant 4. So taking the inverse tangent of this will give us what we actually need. Tangent inverse of 20 minus 30 square roots of 2 over 20 square roots of 3 plus 30 square roots of 2. So those are the answers. If I put them in my calculator, and I did not check my answer, so again, you can check my answer there, but I get 73.7 there. That's a resultant, so that's a force, so that's newtons. And then the angle I get is negative 16.2 degrees. And that's reasonable, negative 16.2. Okay, again, I didn't double check my computations, but it seems pretty reasonable. So that's finding the resultant. All right, now, all of that should be reviewed for you. If it's not, and you're feeling a little unsure, as I said, check out some videos that are out there. Professor Leonard does a good job on the vectors, so you could look at that video. But where it comes into 5C is that we are going to extend all of this to 3 dimensions.